should somebody need it. Excellent. So the first thing we're going to talk about is the properties of point statistics and dispersion. And we're going to, as I said, look at each of these statistics and talk about when they're appropriate, when they're not appropriate, and sort of what are some of the common pitfalls that people fall into with regards to using and applying these statistics in practice. So the first statistic that we spoke about yesterday, last week rather, was the mean, the arithmetic mean. It's something that you're all very familiar with, I'm sure. And there are a couple of, and it's something that you will absolutely come across in your academic careers quite often. And there are a couple of important properties of the mean that I think is worth noting here and making sure that you're aware of these things. Now, this list of things are these important properties that I'm going to be showing for the point statistics and dispersion statistics. They should not be necessarily surprising. These aren't going to be necessarily, at least most of these aren't going to be things that, you know, have you grabbing the back of your head going, oh my God, how did I never know? Rather, these are things that are probably, you realize you know, even though you may have never acknowledged that you know them at the you know, cognizant forefront of your brain. But they're nonetheless very important, and you'll see why they're very important as we go through. So the first properties that we're going to be talking about are the mean. So here I've just reproduced the formula for the mean, and you'll remember the notation that we're using is that we have a variable x, which I'm actually showing here as a bold using this sort of vector notation that you're probably familiar with from your mathematics in undergrad. Is essentially the set of all observations of the variable x, which are x1, x2, all the way through to xn. And the mean, which we define, the sample mean, which we define as x bar, is just the summation of the individual x measurements divided by n. Now, some of the important properties of the mean. So we've got firstly the scaling statistic or scaling property, which is that scaling the data scales the mean. That is to say, if I was to multiply all of my data by some constant k, then I receive the exact same equivalent answer as if I just scaled the mean by k. I'm going to go through these in a little bit of probably over detail because they're going to come up in the next few slides quite a bit, and that way we won't have to go through them every time. Translating the data. So translation is when we take the vector x of our data and we just apply, add some constant c to it. And translation means that translating the data also translates the mean. That is to say that the mean of x plus c is the same thing as the mean of x plus c. If you're not looking at the slides and heard me say that, that was probably very confusing. The sum of the sign differences from the mean is 0. This is an important one. And that is to say that one of the things, and you'll remember that when we discussed our first set of dispersion statistics, the thing that we looked at was the signed difference, or rather the not absolute deviation from a particular point. So this is essentially what we discovered accidentally last week, which was that if we take a point which is in the middle of our data and we sum the signed differences, so not the absolute differences, then we could get a dispersion statistic that turned out to be very close to 0. Now, if the point in which we're summing around happens to be the mean, then by definition, the sum of these signed differences is 0. That's a fundamental property of the mean. And the last of which, the last interesting statistic, or the last important sort of property of the mean is this one, which is that the average square distance between all data and a single point mu is minimized at the mean. So when we spoke about the dispersion statistic that we calculated last week, we just sort of said, let's create a dispersion measure, which is the sum of the square differences with regards to some arbitrary point. And we called that point last week A, you might remember. Here I'm calling that point mu. And what we're saying is that one of the properties of the mean is that the minimum of this sum, or rather the minimum of this sum for an arbitrary choice of mu is minimized at mu equals the mean, the arithmetic mean. And we can prove that. So we're going to go through now just to prove that quite simply. So the way in which you calculate the minimum of a distribution is by taking the first derivative, finding the 0 point, and you've got your minimum. And so what we're going to look at here is we're going to take the derivative of this function with respect to mu. So that's the property that we're interested in. And we get this -2 times the summation of the sign differences. And we're saying that we want to assign that to 0. So we just do the rearrangement, the -2 drops out, and we end up with this summation term here. So if the sum of xi minus mu is the same as the sum of xi minus the sum of mu's. The sum of mu is just n times mu, because there's obviously no x term in here. And that gives us an n mu for this term. And so we can rearrange that, and we end up with mu is equal to 1 over n times the summation of xi, which is, of course, going straight back to the top, the definition of the mean. And so the minimum of the squared distance between any particular point is minimized when that point is the arithmetic mean. Cool. Okay, the next thing that we're going to talk about is similar sorts of useful properties of the standard deviation. And so you'll recall that from last week, we had the definition of the standard deviation, which was this here, or rather the definition of the sample standard deviation. You'll recall that we spoke about there's a difference in what you'll find online for how you formulate this thing called standard deviation. And that's, a bit confusing. Excuse me. The sample standard deviation, so the standard deviation of a sample of points, is defined here as 1 over n times the sum of the squared differences between xi and the arithmetic mean, all square rooted. Or writing that out in a way that's sort of more program notation, it's the square root of the mean of these differences squared. Okay. This is just saying that the unbiased estimator that we have of the standard deviation, of the population standard deviation, is slightly different. It's this n-1 factor instead of the n factor at the front here. And the reason for that, again, I'm not going to go into right now, but it's something that we'll probably talk about in the inference part of this course a bit later on. Start talking about expectation values and a whole bunch of other things. Okay, some very important properties of the standard deviation that are important for you to understand, for you to know. The first is translation. Unlike the mean, translation does not change the standard deviation. That is to say that the standard deviation of x plus a constant c is just equal to the standard deviation of x, the vector of x values. Scaling the data, however, scales the standard deviation in the same way that it does with the mean. So the standard deviation of kx, so where we've multiplied our x vector by some value k, is equal to k times the standard deviation of the data points x. It's an important property. And the last one is the one that you're probably not familiar with, which is arguably the most important. And that is to say, for n observations of an arbitrary variable x, whose standard deviation is s. So again, going back to our just definition of the standard deviation here, sample standard deviation, there can be at most n over k squared data points lying k or more standard deviations away from the mean. So what does that mean? That means that given a particular data set, there is always a maximum number of data points that can exist a certain number of standard deviations away from the mean, given the definition of sample standard deviation and the definition of the arithmetic mean. And that might be a little bit difficult to understand or to comprehend. And so we can sort of prove that as well. Okay, and so the way in which we prove that is we consider some like hypothetical variable, hypothetical variable y, which is just a set of observations. And it's a set of observations of length m. And there are m entries in that vector that are k standard deviations away from the mean. So this is just formulating the notation here that we're going to be using in a second. So you have a data set y. That data set has n elements. And of those n elements, m elements are k standard deviations away from the mean. That means that the fraction of data that are at or beyond k standard deviations away from the mean is just r, which is the fraction of m over n. So this is, again, just a simple notation thing because it's going to be used a bit later. And the last thing that we're going to do is we're going to assume that the arithmetic mean of our data set y, of our variable y, is equal to 0, just because it's going to make the calculation a bit easier. Now, it's worth pointing out, and it's important to recognize, that that doesn't change the generality of what we're about to do because of this thing here. So the arbitrary center, the arithmetic mean of the data set, doesn't influence its standard deviation, and therefore the choice that we've just made to set the arithmetic mean equal to 0 doesn't actually have an impact on the conclusion that we're talking about. The question that's just been posted in the Slido is, does this thing that we're deriving about have a common name? That's a good question. Not to my knowledge. I think it's just one of the properties of the standard deviation, but I might be wrong in that regard. So I'll have a look and find it. But that's a good question. If not, I'll just name it after myself, because why not? So we have the standard deviation y of this vector, and we're going to call that sy, which because the arithmetic mean is equal to 0, is just the square root of 1 over n times the sum of the y values squared. Okay, now this is for an arbitrary data set. Other than specifying that the arithmetic mean is equal to 0, we've not assigned any properties to this data set as yet. So let's do that now. Let's assign some properties to this data set y, and let's say that our goal here is to demonstrate the limiting case, the most pathological possible case that we can come up with. And so the case that we're going to come up with, I'm going to go over to my notepad here for the first time, is we're going to construct a data set that is essentially looks like this. We have 0 here. This is n on the x-axis and y on the y-axis. N on the y-axis, y on the x-axis, confusingly. And our data set is going to look like this. Our data set has n values that are less than n minus m values that are less than k standard deviations away from the mean. And we're going to put every single one of those n minus m values at 0. And the reason we're going to do that is because, as we just defined, the standard deviation is going to be the sum of the y values, and we don't want those data to contribute to the standard deviation at all. So we're going to set them to sit at 0, and therefore they will not contribute to the standard deviation in any manner, shape, or form. We're then going to take the remaining m data, and we're going to put them equally plus and minus k standard deviations away from the mean. So k, sy, k, sy. Okay, and the number of data points in these two things is m over 2 in order to keep the arithmetic mean at 0. Okay, so this is the pathological data set that we're coming up with. And the reason this is the most pathological case that we can come up with is because if we moved these data, or rather we smeared these data beyond KSY in either direction, then that would increase the standard deviation because the summation is happening over the Y values squared. And so this is the most pathological case we can come up with for a particular standard deviation measure. If we then, so we've got these two values essentially, one of which is at 0, y of 0, and the other of which is at, that should be an absolute value of k sy. And so what we can do is we can calculate the, we can then use this very strange data set that I've constructed, and we can calculate the standard deviation. Okay, and the standard deviation for this very weird data set is the summation here over all y values, which is, there should be a missing bracket here, which is 1 to m of the y1 values, which is, so there are m values at k s y1, and there are n minus m values at 0. And these things are all 0, as we just said. So this goes to 0, and we just get the summation from 1 to m of sy rather, squared. And that ends up giving us this formula here. So the standard deviation of this pathological data set is equal to the square root of mk squared sy squared divided by n, which m over n is just r, as we defined it earlier. And therefore, this is the formula that we have. That means that we can square both sides. We end up with s squared y is equal to rk squared sy squared. And we can cancel these, and we end up with r is equal to 1 over k squared. So the fraction of data that exist beyond the standard deviation directly from the standard deviation formula that we just calculated is maximally 1 over k squared. And the important thing is that at no point, other than making this data set as pathological as possible, did we specify any properties of it. So this is true for any data set. There is a maximum number of data, rather a maximum fraction of data that can sit k or more standard deviations away from the mean, okay, for any data set. And this turns out to be very, very important for reasons that we'll see in a little in a minute. Okay. The next property that we're going to look at is that for any data set, there has to be at least one data point that exists one or more standard deviations from the mean. So we just demonstrated that there is a maximum number that can exist beyond a certain standard deviation. And we're now going to show that there is at least one data point that exists beyond one standard deviation. Okay, and the way in which we're going to do that is quite simple. We're going to take our standard deviation formula. Again, we're going to generalize to the mean is equal to 0 and not lose any generality. We're going to then just rearrange this formulae. So we're going to square both sides, multiply the n across, etc., etc. Now, the right-hand side on this equation is the sum of all squared deviations from the mean, which we said is the 0 in this case. The mean is 0. But crucially, the sum of all squared deviations has to be less than or equal to n times the maximum deviation. That is to say that if every single xi value had the same value, which was maximally deviant from the mean, then that number is n times that value squared, right? So if there are any xi that exist below that point, below xi is equal to whatever the number of the constant that we just picked was, then the sum of the squared deviations will be less than this value. Yeah. And what that means is that we can then say that because the sum of the squared deviations is less than this thing, we can then put this inequality back up here, and we end up with n times s squared is less than or equal to n times the maximal deviation of xi squared, and therefore that the standard deviation squared must be less than or equal to the maximum value of the deviation of xi from the mean. So that is to say that there has to be one xi value that is greater than or equal to the standard deviation by definition, because of this formula. Okay, cool. Hopefully that's clearish. We're going to see why these two particular things, so these two properties that we just discussed at the end there, are quite important. The first one, I would argue, is the most important one. So the k standard deviations away thing. But basically what this is telling us is that the standard deviation is quite informative, right? Because by definition, as we just proved, the standard deviation has to be greater than some of the data and less than a fixed fraction of the data. So it has to be informative, essentially, for some measure of dispersion. We'll see why that's going to be important in a couple of slides' time. Okay, so we're now going to recall the median. So we discussed the median last week as well. You'll recall that the median was defined like this. And so we have the median of our vector of x values is defined as, in the case where there is an odd number of elements n, then it's just the element that has an equal number of elements on either side. And in the case when it's an equal number of elements an even rather number of elements in the vector, in the distribution, in the variable, then it's the linear mean of the two innermost values. Like with the mean, the median has a couple of important properties, and these are the same as the mean. So scaling the data by some constant x also scales the median, and translating the data also translates the median. Probably not terribly surprising. We also looked at the normalized median absolute deviation as a measure of dispersion. So the median absolute, you'll remember the normalized median absolute deviation from median was defined as this funny number 1.4826 multiplied by the median of the absolute deviations from the median, as the name suggests. This funny number, you might recall from last week, comes from this normalization. And that means normalization in the mathematical sense, where with that prefactor, the NMAD produces the same value as the standard deviation for normal data, so for Gaussian data in the limit of large n. Again, the NMAD has some properties that are pretty important, and they're the same properties that we saw for for the standard deviation with regards to translation and scaling. That is that the translating the data doesn't change the normalized median absolute deviation from median, and scaling the data does cause a change in the scaling of the NMAD. Okay. One of the last things that we spoke about at the end of last week was the quantile function. The quantile function, you'll recall, was we looked at the cumulative distribution function, or rather the empirical cumulative distribution function, which was the way in which we essentially rank ordered the data and then calculate the percentage of data that sit at various values of x. And we said that the quantile function is the inverse of that. The quantile function is the inverse of the cumulative distribution function. And then we went through a little bit of a discussion about how, well, actually, we can't invert the empirical cumulative distribution function, because you'll remember that it's an empirical function, which is a step function. So it has steps as you go from, point xi to point xi plus 1 to point xi plus 2. You have steps in the empirical distribution function, which means that you can't invert this thing, E, C, D, F. And therefore, what we do is we actually use a linear interpolation between those data, like so, and that's how we calculate the quantile function. You then invert that distribution. Now, one of the things we didn't mention was one of the uses of the quantile function is the definition of what's called the interquartile range. Now, the quartile is as the name suggests, it's a quantile that splits the data into quarters, and so hence quartile. The four standard quartiles that we have when we discuss data are the 0 to 25th percentile, the 25th to 50th percentile, the 50th percentile, you'll recall, is the median. That should say 50th to 75th percentile, and the 75th percentile to the 100th percentile. So these are the standard four quartiles, and the interquartile range is defined as the difference between the 75th percentile and the 25th percentile. So essentially it is the range that encloses these two inner quartiles, yeah, or the middle 50% of the data, thinking about it another way. The IQR is just another measure of dispersion, and one that will become important when we start talking about uncertainties on medians and uncertainties on means, and things like that. The IQR has the same properties as the standard deviation and the NMAD with regards to translation and scaling, so no need to dwell on those for terribly a long time. Okay, so now we're going to get to the interesting part of comparing the statistics. So what is the point? Why do we have, or why are we interested in having different statistics for different different use cases, or why is it relevant that we have a median and a mean, or a standard deviation and an NMAD? Why are these things useful? When are they useful? What are the pitfalls, et cetera, et cetera? So we're going to go through those right now. So we're going to start by looking at central tendency. One of the things that we've done a lot of in the course of the last couple of weeks was assume Gaussian data. That is to assume that we have data that is very well behaved, that is perfectly symmetric, and doesn't have any funny data points, outliers, or anything. But in reality, that's very, very unusual. It's very unlikely that we have purely Gaussian data, despite how much we like to pretend that we do. And so one of the things that we discover when we move away from perfectly Gaussian data is that, in particular, measures of central tendency like the mean are particularly sensitive to the presence of outliers. And this is basically because of one of the properties of the mean that we just discussed, which is that the mean minimizes the average squared distance to all data. And that means that if you have a very nicely compact set of data and then one value out at near infinity, then that data point needs to be minimized in its average distance as well. And that causes very, very high sensitivity to outliers that are unphysically far away from the mean, essentially. So let's sort of look through this using an example data set similar to one that we saw last week. You'll remember last week we discussed or rather we had the data set of the average height of mice in Disney films. We're now going to look at a slightly different data set, but one that is very, very similar in philosophy. And that is to say, we're going to look at a mock survey that's conducted in and around the Disney World Resort in Florida. Now, our mock survey was conducted by a statistician who was working part-time as a wildlife consultant. Very important to know this sort of information. And they're working, and their goal in this wildlife conservation job is to catalog the heights of all mice that sit in the area within and around the Disney Florida World Resort, the Disney World Resort in Florida. Now, being a very conscientious statistician, they do exactly as they're told, and they calculate the average heights of all of the mice in and around the Disneyland Resort, all of the actual animal mice, plus the mascots of Minnie and Mickey. Okay, so we have a data set here that is now a normal Gaussian population with the presence of a bunch of very, very odd outliers. And we want to then say this data set is then handed to us completely blindly, and we don't do any sort of exploration of the data set. Instead, we just say, okay, the first thing I'm going to do is I'm going to calculate the mean height of mice at Disney World. Okay, and I calculate the mean of the mice in my data set and the median of my mice in my data set, and I find that the average height of a mouse around Disneyland in Florida is 14 centimeters. That's a very large mouse. However, the median is around 7 centimeters. So this demonstrates that the mean has been quite susceptible to the presence of these outliers. In fact, if you were to zoom in here, you would see that the peak of this distribution, the true mean of this distribution, is 7 centimeters. Okay? But the presence of these outliers has driven the mean estimate to being unrealistically large, indeed a factor of 2 larger than the true mean. So the presence of the mascots has completely ruined the mean estimate here, but it hasn't affected the median in a significant manner. And so this is demonstrating that the median statistics are considerably less sensitive to the presence of outliers than mean statistics. And that's a very, very important fundamental thing that is important to understand when starting to think about how we characterize data sets. The next thing that we want to look at is the dispersion. And the story becomes even more problematic when we ask the question, okay, the mean was large for the mice data set, for this mice survey, but what about the median? And so we calculate what about the standard deviation? We calculate the standard deviation, and we essentially say, I'm going to calculate my standard deviation of the mice data set. I'm going to calculate the MAD of the mice data set, and I'm going to calculate the interquartile range as well. And what we find is that the standard deviation, of the mice data set is 34 centimeters, whereas the median absolute deviation is 1.5. Now, again, being somebody who knows the actual truth here, I'm going to tell you that the true dispersion of that cloud of real mice, not the mascots, is 1.5 centimeters. And so again, the median absolute deviation here is being very robust in returning the dispersion estimate in the presence of outliers that is catastrophically biased in the case of the standard deviation. And this is where the thing that we went on and talked about for 5-10 minutes or so in the standard deviation becomes really important. Why is it that the standard deviation is so heavily affected by the presence of these outliers? And the reason is because this catastrophic failure is because of this property of the standard deviation that we just discussed. In this data set, the fraction of data that reside in this outlier peak is of the order 4%. Okay? And using our simple, fractional calculation, we can estimate what is the maximum standard deviation that these outliers can be from the mean, given that they make up 4% of the data. And the answer is that they can reside at most 4.8 sigma from the mean. Now, in reality, this hasn't printed. In reality, the actual data set is of order 112 standard deviations from the mean. These outliers here sit about 112 standard deviations from the true mean of the distribution. But the standard deviation physically cannot allow that to happen because they are such a significant fraction of the total data set. And therefore, the standard deviation balloons, and it balloons to a value of 34 centimeters. I think that hopefully makes sense. Okay, so that sort of gives you an idea of how the measures of mean and standard deviation can be heavily biased by the presence of outliers. Okay, what we're going to do now is we're going to sort of change gear a little bit and start talking about how we use these statistics, not just to describe a particular variable, but how to describe differences between different data sets of the same variable. Okay, so let's to sort of further make clear the importance of understanding the data set that we're talking about. We're going to look at a new addition to our data set. So basically, we've got our mice data set that was created by our statistician, and let's say that survey happened in November, which is what the little NOV here stands for. Now, let's say that instead, or rather in addition to this data set, we have another data set that was performed by a different person at the same place, but was done 6 months beforehand, so in May. Okay? Now, this person who did the measurements in May was a particularly proficient statistician, was very, very well respected because of their ability to consistently distinguish between real mice and 6-foot-tall humans in a mouse costume. And therefore, they saw the mascots and said, well, those aren't mice, and don't include them in the data set. And so essentially, we have two data sets now, one that contains the pathological outliers and one that does not. And the first way in which we can compare these two data sets is by just, say, taking a histogram. Okay, so we can take a histogram of the first survey, which happened in May, and the second survey, which happened in November. And what we see is that the first survey shows the same distribution of data at low values, at regular mice height, but doesn't have the presence of this outlier peak. The results of these two surveys, if we ignore the presence of these outliers, is exactly the same. So these two distributions are exactly the same. But if we calculate the mean and median, the mean of these two data sets, we find that the mean of the latter data set, as we saw already, was 14, and the mean of the May data set is 7. Why is this important? Well, let's say that without any additional information, you use the mean to justify or try to understand some causal relationship between what has happened at Disney World between May and November. You would logically come to the conclusion that the activities at Disney World in 6 months have caused the mouse population to increase in size by a factor of 2. Because the mean estimate hasn't recognized the presence of these outliers, and the only thing you looked at, ignoring this plot, was the mean. And so this is simply a sort of a very artificial way of saying something that should be hopefully not very contentious, which is the utmost important thing when you are provided with a data set is to understand the data set prior to trying to do any statistical inference. And so that's one of the things that we're going to spend quite a bit of time on towards the end here. Okay. We're going to now go through and look at how, so we just showed how you can compare two distributions using a histogram. We're now going to look at actual comparing two distributions of the same variable. So looking at a univariate distribution, so just two distributions in the same variable x with different samples, and looking at how we can compare these two things in an effort to try and diagnose problems, to try and diagnose, for example, catastrophic outliers, so that we can recognize that those things are present in the data set and, make our analysis robust to the presence of those failures. Okay. The first thing is the KDE again. And so we've seen in the previous slides, or rather the last week as well, that you can use a KDE, which is sort of a continuous replacement for a histogram, continuous version of a histogram. So again, we can basically take the histogram that we just made from the previous slide, and we can compute the KDE of that particular histogram. And what we find is that the red line here shows the first survey, and now it's very, very clear that there is no information in the first survey out of this outlier peak, because the line is very clearly at 0. And you can furthermore see that the distributions here at low values of the size are almost identical, which I would argue is easier to see with the KDE than it was with the histogram. So the KDE is very, very useful for doing this sort of direct comparison. However, if you had, instead of 2 data sets to compare, rather 20, then having 20 lines over this plot, all of which have slightly different noise and various other things and outliers, can become very, very difficult to understand and interpret. And therefore, it's often useful to not look at the KDEs in this format directly, but instead to look at other types of graphical summarization. Okay, so one such other graphical summarization is what you may remember from high school, which was referred to as the box and whisker plot. And so a box and whisker plot is essentially a graphical tool for summarizing quantiles of the data distribution. And what does that mean? So basically what you can do is you can take a two data sets. So here we have the first survey and the second survey. And what you can see is that given the outliers that are present here, it's very, very clear that this isn't super informative with the current y-axis that we have here because of these outliers. And so just to sort of get an understanding of what's happening with these actual box and whisker plots, we can shrink down the y-axis to instead just contain the overwhelming majority of the data. And this is what we see with the box and whisker plot. So what we've got here is the box section of this this distribution shows you the interquartile range of the data that you have. Okay, the horizontal bar here is the median. So you have the median and the interquartile range. The whisker, so these dotted lines that lead to these bars, these are depending on how you formulate the box and whisker plot, they are variably a certain fraction of interquartile ranges beyond the mean. So essentially, that is to say, if we have, for example, let me go back to just draw something here. So if we have a distribution of data that sits, like this, then our box and whisker plot, so let's just call this X, and let's call this N. So our box and whisker plot has the median, which sits here as the bar, the box, which is the interquartile range, and then the dots and the whisker I want to say the whisker extends to the last data point that is 2 interquartile ranges from the median, for example. And that would give me this data point and that data point. And so that's the whisker. That's how the whisker is defined. And you can basically choose that somewhat ad hoc. And then any data point beyond the whiskers is shown as a point. Okay, so you can see here that in this case, the decision that I made for where to put the end of the whisker means that there is an outlier, in inverted commas, very, very near to where the edge of the whisker is. And in the second data set, obviously, we saw that the outliers were very, very far away, and those were our failed mascots. The last thing to note here is the notch that you can see on the box and whisker plot is something that you might not see on all box and whisker plots. And what that notch tells you is essentially the confidence that I have in where the median sits. And so this relates to the uncertainty on the median. And the uncertainty on the median, or rather what's called the 95% confidence region on the median, is defined using this formula here, which is 1.58 plus minus 1.58 times the interquartile range divided by the square root of the number of elements, the number of data points that are in the data set. Now, where this magic number 1.58 comes from is somewhat similar to the normalization coefficient we saw in the NMAD. It comes from what's called asymptotics, and you don't really need to understand where it comes from, but this is essentially the formula for the confidence region on the median. And that's what's shown by the notches here. Okay, so what we can see from the box and whisker plot here is that essentially the localization of the median between these two data sets is within the notches exactly the same. And so according to the median statistics and the interquartile range and the whiskers, these two data sets are identical, except for the catastrophic outliers, which are shown by the points. And that's the interpretation that we want with this particular data set. Yeah. So that's good. The box and whisker plot has done its job. It's told us that nothing has changed in the intervening 6 months between these two surveys. except for the presence of some catastrophic outliers in the second survey. Sometimes, however, the distribution of data won't be simplistic. It might not be Gaussian in the main body of the population. It might be multimodal, for example. It might have multiple populations that exist at different values. We'll talk about that a little bit more later on. And one of the ways that you can make your analysis robust to the presence of very, very strange distributions of underlying data is using, again, the KDE. But instead of using the KDE in the way in which we plotted it before, which is having just a distribution. So if I go back to what my little plot here, no, I didn't plot it. So what we had before, which was just the distribution on the x-axis with our little outlier bump. Instead, what we can do is we can construct what's called a violin plot. And the violin plot looks like this. And what you can think of the violin plot as, I'm going to draw on my own slides here for the sake of explanation. The violin plot is essentially the KDE. So if you were to tilt your head, then this orange histogram, or rather curve here, so this is now X, and this is the KDE on the y-axis, then that is the KDE. That's the kernel density estimate for this data set in height. Yeah, that kernel density estimate is then mirrored about the center of the distribution here, and that gives you what's called the violin plot. Okay, and so if we were to create the violin plot for both the May survey and the November survey, then we see that the May survey has just this peak at low values of the height, and the November survey has a very strong peak at low values and then has these outlier peaks at higher values. Okay, the utility of the violin plot is that it shows the KDE, and it shows the KDE for many different, possibly many different sets of data in a way that is easily digestible. So we can, for example, shrink down the KDE to just be around the plot, the part of the distribution that has the most data. And when we do that, we get this error, this warning message that says, hey, we removed some data when we made that reduction in y-axis. Just be aware of that. And you can see now that these distributions are actually subtly different, but overwhelmingly they look quite similar. One of the really neat things about the violin plot is that you can compound information into the violin plot in a way that is really easy on the eye. It's really easy to interpret. Now I'm using, you've probably noticed, or you might have noticed, I'm using a very strange plotting function here. You might recall from the first lecture, or the 0th lecture as it were, that I discussed how the majority of the plots that I make use this thing called magic axis. The other very popular tool for making plots in R is this thing called ggplot. Now, I won't go into the details of ggplot now, but if people are interested, then I'm happy to give an additional sort of note on how to use ggplot. And you'll see why it's so popular. It's very powerful. The way in which you use it is slightly different than what you do for a normal function call. It's closer to object-oriented programming, or rather pipe sort of things that you might be familiar with from shell scripts and stuff. But this is just to say that we're creating a plot which is using the information from our data frame, which contains our survey data, and we want to plot the survey versus the height. We want to reduce the y limits to this range. We want to plot a violin plot, and then we want the colors to be classical, and we don't want there to be a legend. And that's what you do to get this violin plot. It's very simple. And the real power of ggplot is the ease with which you can then layer things on top. In that way, it's very much like matplotlib in Python. And so, for example, if I then wanted to add the actual data points, for example, to see where the values lie in each of these surveys on the height axis, then I would just say I want to add geometric points with this particular style, and boom, there they are. So you can see that the KDE is showing you that the data points are starting to peter out here, and that it's basically a solid line in the middle here where there's lots of data. And so you go, okay, well, that's not super useful for me. But wait a minute, we just spoke about the box plot. What about if I instead put a little box plot in the middle here? So that way I've got the KDE and the box and whisker plot all in one. And you can do that again very easily with ggplot by just saying box plot. And there you have it. So now we have the box plot and the KDE together in the distribution. You can see where the outliers in the box plot lie. And all of it is quite easy to interpret, quite easy to understand. So this is the violin plot, very, very useful. The last type of plot that we're going to talk about from memory is what's called the quantile-quantile plot. So you'll recall that we talked about the quantile distribution already a couple of times in this lecture and last week. The quantile-quantile plot does exactly what it says on the tin. It plots the quantiles of one distribution versus the quantiles of another distribution. And that might seem or sound a little bit strange, but it turns out to be an extremely powerful way of discerning differences between two univariate data sets, two data sets that have the same variable, and you're plotting different samples of them. So again, we can just use base R now to plot the QQ plot. And we can look at the QQ plot of our May survey and our November survey. And what we find is that you see a huge scattering of the data points down here. And then all of a sudden, the November survey jumps to very large heights, and these are our catastrophic outliers. Now, this isn't really easy to understand because the majority of the data have been squashed down the bottom. And so what we can do is we can instead sort of focus ourselves on the one-to-one region, which is what this red line is showing. And so instead, we can plot with a fixed aspect ratio. So one step in X is one step in Y. And we can plot it around the region where the majority of the data is. And I've converted the points to a line now. And what you can see is that the overwhelming number of quantiles of the heights of the May survey and the November survey sit on the one-to-one line. That is to say that the quantiles of the May survey are the same as the quantiles of the November survey until you get to very large, until you get to the catastrophic outliers, and that's where it flies off to infinity. Now, the utility of the quantile-quantile plot is that it encodes a lot of information, more than you probably understand just by looking at this example. So let's construct a couple of just fake data sets to give you an idea of what the quantile-quantile plot shows. So let me show you, let me make again just a number line here on my little pad down in the bottom right. Let's call that, X, and we'll put 0 in the middle. And the first data set that I've constructed is just a Gaussian with a center at 0. Okay. The second data set is a Gaussian with a mean at -2. And the third is a Gaussian with a mean at 2. Okay, so these are our three data sets: 0 mean, negative mean, positive mean. And I'm then going to plot the QQ plot for these different data. And what you can see is that if I plot the 0 mean versus the positive mean first, that the 0 mean is on the x-axis here, the positive mean is on the y-axis, and you can see that just by the values. I haven't plotted the labels on the x and y-axis here, which is extremely naughty of me. I'll make sure that I change that in the lecture notes so that you don't learn bad habits. But that is to say that you can see that the positive shift in the mean has caused a shift with respect to the distribution and the one-to-one line. You see the opposite shift when you use the comparison between the 0 mean and the negative mean data. And if we look at the difference between the positive mean and the negative mean, then that shift gets greater again. So a shift in the mean causes a very significant lateral movement away from the one-to-one line in the QQ plot. Important fact. The second thing we can do is say, okay, that's the mean. What about if the distributions have different dispersion? So now we can construct three new data sets which have a standard scatter. So here we're now, let me remove these plots here. Oh, no, I'm not going to do that. Instead, I'll just draw them up here. So let's now look at a different data set where we have, I shouldn't have done that. Anyway, we have 0 here again. And this time we have one data set which has a standard dispersion, one data set which has a very small dispersion, and another data set that has a very broad dispersion. Okay, those are our 3 data sets. And so the standard scatter data set, we plot against the small scatter data set. And what we find, again, is that now instead of shifting away from the one-to-one line, what's happened is the tilt has changed in the one-to-one line. Okay? And again, if you do this the same with the standard scatter and the large scatter, again, you see a change in the tilt of the QQ plot with respect to the one-to-one line. And that tilt becomes more significant if you compare the large scatter and the small scatter. So this is related to the difference in dispersion between the 2 data sets. So the deviation with respect to the distance to the one-to-one line dictates a shift in the mean, in the median. A difference in the slope with respect to the one-to-one line dictates a difference in the dispersion. And the last thing that we can look at is what happens if we have outliers. So we can construct a normal distribution with data, which is just a Gaussian, and then we can construct the same Gaussian, but we can add in 100 random outliers. And we plot the QQ plot of this distribution, and we see this happens. So you have a incoherent deviation away from the one-to-one line caused by a difference in the outliers of the 2 populations. So the QQ plot is extremely powerful. It tells you the difference in mean statistics, median statistics, the standard deviation, the scatter, the dispersion, and the outlier rate, all in a very, very visual manner. So I can now construct, yes, absolutely. So the question is that can the size of the 2 samples be different? And as you can see, what I've done here is I've actually created 1,000 elements in the first data set and 1,000 plus 100 elements in the second data set. So they can have totally different lengths, numbers of observations per sample, and they still are it's still totally perfect, totally fine to use. And that's because the quantiles are calculated of the data set, not using the individual values within the data set. Great question, great question. So the last thing that I'm going to do is I'm going to tell you that I've constructed a fictitious data set. My fictitious data set has value y, is called y, and the expectation that we have as astronomers going and physicists going into our analysis is that the distribution of y should have the form of a Gaussian with mean 0, standard deviation 1. And so what I'm going to do is I'm going to construct a model distribution of data, which has mean 0, standard deviation 1. And then I'm going to compare the QQ plot, or going to construct the QQ plot for that model distribution of data and the true data set Y. And this is what I get. And the question then becomes, what, given this plot alone, can you conclude about Y? And so we can basically go through and we can say, okay, there's a slight offset with regards to the mean, to the distribution with regards to the one-to-one line in absolute terms. So there's clearly a slight difference in the mean and the median of these 2 distributions. So the Y data don't have a mean that is equal to 0. First things first. Second thing, the slope of this line is not equal to 1-to-1. So there is a difference in the scatter between the data and our assumed scatter of 1. Second point. Third point, we see an incoherent deviation from 1-to-1 at high and low values of the QQ plot, which demonstrates that there are outliers that do not fall in the Gaussian model that we've constructed. And so with this plot alone, we can already start to diagnose a bunch of really important things about our data set. So the QQ plot, very, very important. We're going to see a lot more of it a bit as we go through the probability section of this course. Great. I hope that's been clear. We're now going to leave comparisons of distributions of one variable behind, and we're going to start looking at distributions of two variables or more variables. And the primary way that you compare distributions of two variables, so how do I compare observations in X and Y, is by plotting what's called the scatter plot that you've all absolutely seen at some point, because I plotted it in the last 2 weeks. And so what you can see here is I've created a data set. My data set is made up of, again, just Gaussian data, random normal data of 1,000 elements. And it has one variable X, which has a mean of 0 and a standard deviation of 1. And it has a variable Y that is also Gaussian, but has a mean of 100 and a standard deviation of 1 as well. And what you can see is that you have a Gaussian distribution, sorry, a random sort of circular scatter plot. But I mean, looking at this, it actually looks like it might be a little bit squashed, right? So if you didn't know that these two data sets came from something which had the same dispersion, you might look at this visually and say, oh, well, that could be slightly different dispersion. But that's kind of a trick of the eye because we're not using the same range on the X and the Y axis. We haven't used the same dynamic range, the same aspect ratio in this plot. So the first thing that you want to do is always be aware of the scales of the axes. Because if it turns out the y-axis covers, 10 more units than the x-axis for data that you think should have the same dynamic range, then you can trick yourself into finding correlation when there is none. I'll talk a bit more about that in a minute. So the first thing you can do is always set the aspect ratio to 1 for data that you think should have the same dynamic range, that should have roughly the same scatter. And if we do that, indeed, we see that this then becomes a little bit more sensible and looks a little bit more circular spherical. For data with very different aspect ratios, using a fixed aspect ratio of 1 doesn't work for obvious reasons. So the question is, what do we do in order to measure or look at the relationship between variables that have very, very different dispersions in one variable and the next? Well, the first of which you can do is you could plot with two different y limits on the x and y axis and tailor those to your own benefits. So that's the first thing you could do. You could tailor the x and y axes by hand in order to get sort of a roughly similar sort of dynamic range. Or you can plot the data in what's called standard coordinates, or if you're a machine learning person, then this is what's called whitening the data. And so what standard coordinates refers to is taking a data set and transforming each variable within that data set so that it has a mean of 0 and a standard deviation of 1. And using the standard coordinate system, you can then compare directly by eye relationships between different data sets, between different variables rather. So again, we can take that same data set that we just had, which has a very different dynamic range. So we have a standard deviation of 50 in the y variable and a standard deviation of 1 in the x variable. We can convert that distribution to standard coordinates just using the scale function, which converts every variable in the data frame to a standard coordinate system. And we can then plot the standard coordinates, and lo and behold, everything looks honky-dory again. Everything looks good again. So standard coordinates are very useful. We're actually going to use these quite a bit later in the probability section of this course, but we'll talk about that a bit later. The next way that you can plot distributions of two-dimensional data in a way that's useful and interpretable is using, once again, the KDE. So you'll hear that KDEs are quite popular. They're quite useful. They have a lot of uses. And this time we're going to plot the two-dimensional KDE. So we're going to plot the kernel density estimate using a two-dimensional kernel in this case, which is a Gaussian, a two-dimensional Gaussian. So it has a bandwidth in X and a bandwidth in Y. And we're going to plot an inbuilt data set within R, which is called the faithful data set, which shows the correlation, or rather a set of observations of the time of eruption of the Old Faithful geyser in Yosemite National Park in the US versus the time that you have to wait until the next eruption after that eruption. And the first thing you can see is that this thing is bimodal. And the second thing that you can see is that it's, there's some trend here, right? And so plotting the kernel density estimate is useful because there's lots of data in here that you then want to smooth out into a distribution that is useful. to interpret. And so you can really pull out the bimodality by eye using the kernel density estimate. This KDE, 2D KDE, I've made using one of the magic axis functions, magcon. But as always, ggplot has another, and also is able to do the kernel density estimates. And the way in which you can do a kernel density estimate in ggplot is using this just geom density 2D. And so here I've plotted the scatter plot of the data set from Old Faithful, and then I've overlaid the two-dimensional kernel density as contours. If instead of contours, I wanted to use, for example, an image like we had sort of in the background of the magplot thing, the magic axis version, then we would use this 2D density filled, very simple again, and you get this really sort of pleasing, aesthetically pleasing plot, which I'm sure will please the Python affiliates in the audience, because this is sort of the standard Python color bar that you can see here. And you can then obviously overlay both. You could have both, for example. So you could have the 2D kernel density, the scatter plot, and the contours all together. All right, so this is just a demonstration of how you can use the kernel density estimate in 2 dimensions as well as in 1 dimension to demonstrate the relationships between variables. And again, it's very, very useful at pulling out things like bimodalities or multimodalities in the data. So data that have multiple peaks in the density distribution. Great. There we go. The next thing that we're going to talk about is pretty important. So how do we summarize relationships between 2 different variables? So as we just saw with the Old Faithful data set, we have a distribution that appears to have some sort of relationship between the eruption length and the waiting time, in that, as one of them increases, the other one increases. There's also some interesting, bimodality here, suggesting that maybe there's some additional thing that's going on that we don't quite understand or we can't probe with this particular data set. But there's clearly something going on with the relationship here. There's clearly some correlation point we're going to see in a second. Tried not to use the word correlation until now. There's clearly some relationship between these 2 data sets. How do we quantify that relationship? Well, the first way that we can quantify the relationship is by looking at what's called the covariance. And that is to say, the common variance between the 2 data sets, or how the 2 data sets vary together in the same sort of way. And so we've previously looked at the concept of the variance. You'll remember the variance is just the square of the standard deviation. And the covariance of 2 variables is just defined as the joint variance of 2 variables. Now, it's defined in this way. Why it's defined in that way, you don't really need to understand for the moment, but what we can see is that this is the formula. So the covariance of variable x and y is the mean of the dispersion of the signed dispersion of x with regards to the mean of x, multiplied by the signed dispersion of y minus with respect to the mean of y. The reason that you can sort of verify that this is a sensible formulae is because you can ask the question, what is the covariance of a variable with itself? And in the limit where you have the covariance of a variable with itself, this thing reduces to the mean of the squared variance, squared dispersion between the data and the mean, which is obviously just the standard deviation that we have up here. So the covariance of an object with itself is the variance, which makes sense. And the covariance of 2 variables is then defined in this way. So we can look at our faithful data set and we can calculate that the covariance of that data set is 13.977. Well, 978. But that number isn't really meaningful to us. I mean, it might be meaningful to somebody who understands what the covariance is in physical terms, but for the moment, that's just really a number. And I don't know what the scale of that number is. I don't know what it's supposed to be. And most importantly, if I scale the data, so if I convert the data to standard coordinates, that number changes. So the covariance changes when I scale the data, which is a bit weird. Or rather, I don't necessarily see how that can be super useful if I want to learn something intuitive about the relationship between two values, between the two data set, the two values that we have. The reason that that happens, or rather, let's not talk about that for a second. In order to sort of remove this variability or the susceptibility to the change in the covariance with a scaling of the data, we can calculate instead what's called the correlation. And the correlation, or in this case, what's called the Pearson correlation between two variables, is defined as the correlation of X and Y is equal to the covariance of X and Y divided by the standard deviation of X multiplied by the standard deviation of Y. And what that does is it removes that sensitivity that we saw here. And what happens is that normalization by the standard deviation of X and the standard deviation of Y creates a value that varies between -1 for perfectly negatively correlated data and 1 for perfectly correlated data, and 0 for data that show no correlation, no relationship. So let's again calculate the correlation now between the faithful data set in eruptions and waiting time. And what we find is that the correlation of the old faithful data set is 90%. So it's very, very highly correlated. You can actually, we did this using the formula here just to demonstrate that it works. So I've just the covariance of X and Y divided by the standard deviation of X times the standard deviation of Y gives us this. We actually have a correlation, Pearson's correlation function in R, which is just called core. And again, doing the exact same thing gives you the same result, thankfully. This then sort of leads us into, well, this is the correlation between two variables, any two variables, X and Y. If we have a data set that contains many variables, X, Y, Z, or rather X1, X2, X3, all the way through to XP or XN, we can then calculate the covariance and the correlation between every variable and every other variable. And that gives us a lot of numbers, and those numbers can then be used to construct what's called the covariance matrix. And what the covariance matrix is it's this thing here. So the covariance of a data set, capital Omega, is the variance of X1 on the diagonal, the variance of X2 on the diagonal, all the way through the variance of Xn on the diagonal. And the covariance of X1 and X2, X1 and X3, X1 and X4, all the way through to X1 and Xn on the top row, X2 and X1, X3 and X1, X4 and X1 on the column, all the way to Xn and X1, and obviously then filling out until you get to the covariance of Xn and Xn, which is just the variance of Xn. Computing the same thing now, but using the correlation instead of the covariance gives us this thing, which has ones all along the diagonal. That kind of makes sense because the correlation of any data set with itself ought to be perfect. And then you have the correlation between all the other variables in the off-diagonal positions. And so this gives us the correlation matrix and the covariance matrix of any data set. So we can construct the covariance matrix of the faithful data set and the correlation of the faithful data set here. And we find that the covariance data set, so this is the variance of the eruptions is 1.3, and the variance of the waiting time is 184 minutes. The covariance of the eruptions and the waiting time is 13.9, and it's mirrored on the off diagonals because the covariance of X2 and X1 is the same as the covariance of X1 and X2. Yeah, you flip the positions, it doesn't change the covariance. You can, and then you can construct the same thing for the correlation function. You see you have these ones on the diagonal, and you have the correlation between the eruptions and the waiting time on the off diagonal. So these are two really important matrices that turn up a lot in statistics. We're going to be looking at them a bit later. Now comes the part where we say, why is the correlation dangerous? The correlation is dangerous for a couple of reasons. The Pearson correlation, let me increase the size of this. The Pearson correlation is a very good measure of linear correlation between monotonic data sets. What does that mean? That means that if you have perfectly correlated data, that are monotonically increasing, you always get a Pearson's correlation value of 1. If they're monotonically decreasing, you always get a Pearson's correlation of -1. If there is some scatter, then the value varies from 1 to 0 when there is no correlation to -1. But if the data set isn't monotonically increasing, the Pearson's correlation function can go very, very weird. And so you end up with 0 correlation between these data sets where you've clearly got some trend that relates the two data set, the two variables. One way that we can try and say, well, maybe there's a way in which we can remove some of the sensitivity to the non-linearity of data is using what's called the Spearman rank correlation. And what the Spearman rank correlation does is it takes the data, which is non-linear. So let's create a non-linear data set. So we have a variable X, which is just a normal Gaussian data set. And then Y is perfectly correlated with X. That is to say that when you know X, you perfectly know Y because it's just X to the power of 3. And we calculate, we plot this data set, X versus Y, and we then calculate the Pearson correlation between these two variables. Now, we just said knowing one means we perfectly know the other. So the correlation between these data sets is perfect, but the Pearson correlation between X and Y is 0.7. And that is because this isn't a linear function. Okay, and the Pearson correlation measure is designed for linear data. The way in which we can get around that susceptibility to nonlinear data is using the rank ordering of the variables, and that is the Spearman rank correlation. So what it does is it takes the X data and it says, I want to know the order in which the variables X fall, and I want to know the order in which the variables Y fall. And because this is perfectly monotonically increasing, the first X is the first Y. The second X is the second Y. The nth X is the nth Y. And the, infinite X is the infinite Y, the infinite -1, right? And so the Pearson's correlation of the rank ordering of the X and Y values is perfect, is 1. And this thing, the Pearson correlation of the rank ordering of the variables, is the Spearman correlation, the Spearman rank correlation. And so if we calculate the correlation of now our observations, X and Y, but using method is Spearman, we get perfect correlation, as we expect, which is good. So the Spearman correlation doesn't have the susceptibility to non-linear data. So let's then say, okay, we've got this new thing, the Spearman correlation. Let's see if the Spearman correlation can recover some of the information that we lost with the non-monotonically increasing data, what we saw in our figure, back here. So let's see if we can take this value, this function here, and see if the Spearman rank correlation is able to give us something more meaningful than 0 for this data set. And so we construct that same data set here. We then calculate the Pearson correlation and the Spearman correlation, and we find that they both have 0 values on the off diagonals. So the Spearman correlation is also not able to recover non-monotonically increasing data, the correlation between non-monotonically increasing data. Okay? So beware correlations. Beware correlation coefficients, beware correlation measures, because they do not function well for non-monotonically increasing data. And one way that you can kind of intuit why that happens is essentially because these correlation functions, these correlation measures are telling you whether or not perfect knowledge in one variable informs you about the other variable and vice versa. Right? So does perfect knowledge of X tell me about Y? Yes. Does perfect knowledge of Y tell me about X? Yes. Therefore, the correlation in this data set is very high. Does perfect information in X tell me about Y? Yes. Does perfect information in Y tell me about X? No. Right? Because now for a particular value of Y, I can have two values of X. And therefore, this thing is, your perfect information isn't reciprocal. And that's sort of one of the ways I think to think about the cause of the difference between the correlation coefficients and why they don't function for non-monotonically increasing data. The next really important thing is about interpreting correlations. So we as people, as humans, are terribly good at finding correlations between data and interpreting them as meaningful. Okay, so here I have an excellent example of two completely unrelated objects. So the divorce rate in Maine and the per capita consumption of margarine in the United States. And the correlation between these two things as a function of time is very, very high. It's about 80%, 90%. Okay, now, if we were to read this, then one might say that therefore eating more margarine in Los Angeles in the United States will invariably lead people to have more divorces in Maine. Now, obviously, that's complete nonsense, right? This is a totally spurious correlation. And spurious correlations happen. And they don't just happen rarely. They happen with increasing frequency with the smaller the number of observations you have and the greater the number of variables you measure for each of those observations. So let's take an example from this thing here. Let's say I want to know there are 10 variables, there are 10 observations here, right? 2000 through 2009 in both of these data sets. Let's take a rough estimate of how many variables we would have to measure that are perfectly random before we pick up any two variables that are correlated at 80 to 90% or more. And we can do that quite simply just with a really basic sort of probability simulation that I've not shown here. But it turns out that with perfectly random data, I can pull out an 80% or higher correlation 6.5% of the time. That is to say that if I was to measure 100, 150 observations, 150 variables of 10 observations, then I'm very likely to find a 90% correlation between two of those perfectly random variables. This is problematic, even in the case of perfectly random data. Okay. However, most of our data is not perfectly random. And that means that not only do we find these sort of spurious correlations because of just random fluctuations, but we also get spurious correlations because of what are called confounding variables. And what confounding variables are essentially variables. So going back to my plot here, variables where we have two variables, X and Y, and we plot them on a plot. And we find that there is a correlation between those two variables. Now, the sort of implicit drive that we have is to assume that that means that X causes Y, or Y causes X, vice versa. But there is absolutely nothing to say that there doesn't exist a different variable Z that creates X and creates Y. And therefore, that you get a correlation between X and Y that is purely driven by the fact that they are both governed by some unknown variable Z. And that unknown variable is what's called the confounding variable. Okay, so we can actually demonstrate this really simply. by doing exactly that simulation. We can create a variable z that has just Gaussian behavior, mean 0, standard deviation 1. We can then create a new variable x that is a simple function of z plus some noise. And we can create another variable y that is also a function of z plus some noise. Now, crucially, x and y know nothing about one another. Yeah. If I was to modify the way in which x is generated, y would have no knowledge of that. And therefore, they are totally unrelated. However, if we then plotted x and y and calculated the correlation between these two variables, we would find that they have a very, very significant correlation. And that is exclusively because they are susceptible to a confounding variable. So, if you learn nothing from this course except for one thing, it is that correlations between variables are absolutely no grounds for understanding or believing that there exists a causal relationship between these two things. And so this is where that very, very famous saying that you've probably hopefully heard comes from: correlation does not equal causation. These are very fundamental. This is a very fundamental tenet in statistics that is important that we all understand. Okay, cool. We've hit an hour and a half. Now, the rest of this lecture what I have in the rest of these slides is basically us going through a data set that I'm going to present. Now, I'm happy to let the group decide whether or not you would like to do this at the beginning of next week, or you want to do this over the next half hour. Continue now. And yes, no. Do not allow select multiple options. Okay, so I'm going to let this up to the Slido to decide. So please give us your opinion of whether you would like to keep going now or you would like to continue on this bit next week. I will say that this bit is a little bit more fun. But I understand that there's been a lot of information, and so I totally understand if you would prefer to do this next week. So that's totally fine. So we have of order 24 people online. So I'll wait until we have a few more responses, and once we have at least half the responses, then we'll make the decision. It's looking like there's a pretty reasonable preference, 2-to-1 for no, which is totally fine, as I said. So in that case, unless the yeses make a very, very startling resurgence in the next 30 seconds while I'm talking, we will end here, and we will continue at the beginning of next week with talking about how we actually do all of this in practice and how we go about employing the statistics that we've learned. Now, as a teaser, as I've said here, the way in which I've decided we're going to employ our education about statistics and what we've learned so far is that I've selected a data set for us to use, a data set that I think is extremely relevant to all people studying the natural sciences living in Germany in 2021. And that data set that we're going to be looking at is the pizza sizes from 2 Australian restaurants in 2012. So we have this data set that gives us the distribution of pizza sizes in Australia in 2012, and we're going to data mine that data set and figure out what we can learn about the sizes of pizzas in Australia in 2012. So that's what we're going to be starting out with next week. I'm not going to give you any more information about that particular data set because I want us to be going into this blind. And I guess that's where we will end here today then. So if people have any more questions, then feel free to add them to the Slido. Again, the Slido is going to be open for the remainder of the week. And hopefully you've all seen that on the Moodle, I've added both the lecture notes in HTML format and in PDF format, in more of a sort of a handout format. And I've also opened question and answer forums in the Moodle. Now, what I've been doing is I've been taking the questions that have been posted in Slido and reproducing them in the forum with the answers that I've given. But you should absolutely feel free to provide more questions as you like on the Moodle in those forums, and you'll see that I'll respond to those as we go through. Okay, yeah, so as I said, that's where we're going to leave it today. Thanks very much, everybody, for joining. If you have any questions, then feel free to stay on the line and ask me. But otherwise, feel free to sign off now, and we will see one another again in a week's time. Thanks all.